Hello, this is Said. I am one of the members of Big Data Research Lab in Wayne State University, and I'm working under Dr. Xiang Lu, and I'm going to present my master's defense. This is a rehearse for my master's defense meeting. First of all, I'd like to appreciate Dr. Lu as my advisor and Dr. Rickley as my co-advisor and my committee members for accepting this invitation. In this thesis, I've been focused on a statistical approach to performance comparison of predictive models and predictive algorithms, and my focused application is in resistance spot welding. Requirements of cars is ever increasing. For example, car safety, fuel economy, and structural integrity of cars are some of ever increasing requirements. And in order to meet these requirements, car makers have several solutions. One of the most important solutions are design and development of new materials like advanced high-strength steels. Advanced high-strength steels currently are used very widely in car-making industries. Advanced high-strength steels are welded by resistance spot welding technologies. These methods are economic, flexible, and fast. A typical car has 3 to 7 thousandths of RSW joints. A typical RSW process involves a stack up. A stack up is the combination of sheets, upper sheet and lower sheet, that should be welded by electricity flowing through the electrodes and by the force exerted by the electrodes. Finally, a nugget will be created in weld zone, and this nugget is responsible to join these two sheets. And geometrical dimensions of nugget is the most significant feature in order to analyze the quality of resistance spot welding weldments. However, resistance spot welding operations have some challenges, and we as engineers should find solutions for these challenges. RSW is a complex process that returns highly inconsistent welds. So, in order to tackle this inconsistency issue, we need highly efficient weldability assessment models. Weldability assessment solutions are typically of two kinds: traditional solutions and modern solutions. Traditional solutions include physical testing, that these tests are realistic but costly, time-consuming, and require more resources of material. Another solution is modern data-driven solutions. These solutions are less costly, but prone to error, and also other advantages of these solutions are economic features. These solutions are fast, and these solutions do not require huge amount of materials as physical tests require. Modern solutions themselves have their own challenges. Some of the challenges related to data of resistance spot welding operations. RSW data is highly inconsistent. And also, relation between process parameters are highly nonlinear. Also, building and selecting efficient predictive weldability assessment models, or PWA models, is challenging. In order to tackle this challenge, we have adopted a strategy that is try and see. So, based on this strategy, different models will be tried and we'll see which one works better. I should add that there is no direct answer to this question, which model works better in resistance spot welding applications. And this result is obtained through literature review. Our goals and approaches in this thesis. In this thesis, our goals are summarized as follows. First, design and development of a deep neural net model for resistance welding operations. This is our contribution to existing models in the literature. So many models like support vector machines, like shallow neural nets, like GAM, random forests have been tried in resistance spot welding applications. However, per our literature review, there is no result for deep neural nets. The second objective is design and development of a scientific framework to assess predictive performance of PWAs, or predictive weldability assessment models, based on statistical principles. And finally, efficiency of implementation platforms in big data scenarios will be assessed. Our approach to scientific performance assessment is, first, to build a pool of predictive models that are very common and popular in literature of RSW. Second, using bootstrapping techniques. And accompanied by 2 sample t-tests and Levens tests, we will apply these techniques to assess predictive performance of predictive models. And to analyze efficiency of implementation platforms, like in big data scenarios, first of all, we've chosen R as an in-memory implementation platform, and DataView as a big data framework. Then, using Monte Carlo simulation techniques, we have increased the size of our data set. In fact, we synthesized our original data set to create a big data set. And using DOE techniques and analysis of variance, we compared predictive performance of R and DataView framework in big data scenarios. Here is the backbone of this thesis. I'm presenting here the thesis roadmap. Based on this roadmap, first of all, resistance spot welding data, or so-called RSW HSS dataset, is analyzed by descriptive analysis. Through descriptive analysis, major statistics are recognized, major statistics like means of groups, variances, and so on. Also, descriptive diagrams like scatter plots will be returned. And finally, as important output, significant features will be recognized based on vote-based feature selection technique. After doing descriptive analysis, we'll be focusing on a predictive analysis. In predictive analysis, first of all, the entire data set is partitioned to train and test sets. Using train set, a pool of common and popular predictive models in the literature are trained and validated through K-fold validation technique. Where I've chosen K as 10 as a very common option in the literature and in the applications. Then, pool of the models is trained and validated. Finally, a test set, a partition from Original data set is applied to assess accuracy of predictive models in terms of mean absolute error. As it can be seen, using this approach and applying just one data set as test set, we will have finally only one MAE as performance assessment measure. And based on our statistical knowledge, we know that only one observation like MAE in blue box cannot be scientifically used to compare different models because it may happen by chance. So, in order to tackle this problem, we have used bootstrapping technique. Based on bootstrapping technique, the test set is bootstrapped B times 2, and these bootstrap test sets are applied to generated models to evaluate BMAEs. So, by applying B bootstrap test sets, we will have B number of MAE measures. And so, based on this, we can create sampling distribution of MAE. By doing this, we can compare statistically our predictive models. Comparison includes comparison in terms of accuracy and comparison in terms of variability. To conduct comparison tests, we have used t-test hypothesis testing. And to compare variability, we have used Levens test. Finally, superior predictive models will be determined. And a superior predictive model is a model that has maximum accuracy and minimum variability. So as our first step, descriptive analysis of a resistance spot welding dataset has revealed that major statistics, significant features, and descriptive diagrams. So our first steps, results of our first steps can be viewed in next slides. Here is the scatter plot of resistance spot welding dataset. In this dataset, we have recognized 12 different combinations or stack-ups, including different thicknesses and different materials. And these stack-ups are grouped by their features. As important observation in this plot, we can see that resistance spot welding is highly inconsistent because for given material and given stack-up, nugget width can be highly different. So, for example, for this group, we can see that it is around 3. It can vary from around 3 up to 9 millimeters. Applying feature engineering techniques, we have recognized significant features of resistance spot welding dataset. As we know, different feature selection techniques result in different subsets of significant features. For example, dropout techniques applied in deep neural net models result in this set of significant features. On the other hand, selection based on hill climbing will result in this subset of significant features. So not only the length of subsets, but also the rank and the order of features are different. We have noticed that A13, as coded weld current of resistance spot welding process, is recognized as a significant feature in all techniques. So, in resistance spot welding, weld current is a significant feature. This finding is in complete agreement with reports of researchers in the literature of RSW. After conducting our vote-based feature selection technique, we are going to analyze our predictive steps. First of all, a pool of predictive validability assessment models involving 10 different models is created. If you notice, we can see that from each class, we have selected 2 models. For example, from neural nets, 2 models from tree-based models like CART and random forest, 2 algorithms from k-nearest from lazy learning methods like KNN and K-star, and so on. Then this pool is trained by train set and test set, and these are the sizes of train, test, and original data set. Finally, generated models are tested by the original test set, and the original MAE is returned. As discussed before, based on one test set, we cannot infer any statistical hypothesis, and in order to have a statistical inference, we need many observations. So since we do not have many original test sets, we are using bootstrapping technique to synthesize many test sets. So we bootstrap the original test set B times. B is equal to 5,000. And totally, we conducted 50,000 experiments to generate MAEs. And finally, for each model, we generated 5,000 MAEs. One is original MAE, and the rest are all bootstrapped MAEs. And based on this bootstrapped and original MAEs, we create a sampling distribution of MAEs for each model. So totally, we will have 10 distribution of samplings for each, for the pool. Here is the result of distribution of MAEs. And we can observe that sampling distributions are normally distributed. Here, the models can be compared based on their normal distribution plot. However, even at this step, we have not conducted any statistical hypothesis testing. So, intuitively, we can observe that DNN model outperforms other models, other shallow models like support vector machine, and it is the best performing model. However, in order to show that, we are going to use statistical hypothesis testing, and we are proving that DNN has the best performing conditions. Also note that true value of MAE is 0 because an ideal model has 0 MAE and 0 variability. So the smaller the distance between the mean of these distributions from the 0 baseline, the better. So a model is performing better if has a smaller MAE and is tighter in predictions. In order to conduct our comparative analysis, sampling distributions are used to conduct comparison tests. Comparison of prediction accuracy is conducted by using t-tests or two-sample t-tests. And comparison of variability is conducted by Leibniz test. Before conducting our experiments and providing our results, first of all, I'm flashing back to the definition of accuracy and variability. Accuracy, or so-called bias in statistics, is the degree of closeness of average value of predictions or measurements to the ideal or true value of observed or standard observations. Ideal value for MAE is 0. This is our baseline. And variability, or so-called precision in statistics, is the degree of spread observed in predictions. And ideal spread is 0 spread. So ideal model is a model that has 0 error and zero variability. So this is our baseline as our ideal model. In order to conduct our t-tests, we have used this hypothesis testing. Null hypothesis is MAE of model A. Model A represents two columns. Is equal to MAE of model B. Model B representing, or B index represents the name of models in rows. And the alternative hypothesis is MAE of model A, or columns, is smaller than MAE of B models. So, conducting this experiment and comparing the t-tests, we have observed that DNN, or deep neural net, outperforms all other predictive models in terms of accuracy, and support vector machines have the least and worst case scenario in terms of accuracy assessment. In order to conduct variability comparison, Levens test has been employed. In Levens test, the null hypothesis says variance of model A is equal to variance of model B, and the alternative hypothesis is variance of model A is less than variance of model B. We conducted Levens test, and the results show that deep neural nets are less variable compared with other predictive models. However, if we select a confidence level as 0.1, KNN model will not be defeated by deep neural net. So, again, flashing back to our normal distributions of performance and sampling probability density. Now, with more confidence, we can state that deep neural net outperforms other models in terms of accuracy and variability in predictions. Also, we can observe that lazy models like k-nearest neighbors and k-star are followed by other models like random forest, and the top 3 best performing models can be ranked as follows. DNN is the first, then k-nearest neighbor has the second top performance, and k-star has the third top performance. As mentioned before, not only we analyzed our models and pool of models in regular scenarios, we also extended our research to big data scenarios, such that we have analyzed and we have researched which implementation platforms work better in big data scenarios. In other words, this question posed: does implementation platform matter? So we are going to research if more efficient implementation platforms are important in resistance spot welding applications. First of all, we should analyze that. Is there any possibility for resistance spot welding data to be big or to become big? The answer is yes. So how? Let's see it. Over the years, resistance spot welding data can accumulate, so they can become big. So this is first we. Also, there are some applications that we need high-speed transferring of data from clouds to gadgets and job shops. So it is second we. Resistance spot welding data can be accumulated and harvested from different resources. So this is third we. And also, we have fourth we, because as mentioned before, RSW data are highly inconsistent, and so they have high veracity. So it can be observed that resistance spot welding data can be big or can become big. From big data literature, we know that traditional and non-distributed analytical frameworks are inefficient in big data scenarios. And we need more efficient frameworks like Apache Spark and other frameworks like big data frameworks like DataView to analyze big data scenarios. In this research, we chose DataView to use in our big data scenarios. DataView is a big data workflow system that can manage data analysis tasks and processes. Also, it provides cloud computing facility, and it has rich, sophisticated machine learning algorithms supported by DataView. More information regarding DataView can be obtained by visiting the website given in this address. As mentioned before, we need to extend our research to big data scenarios, but this task has its own challenges. For example, RSW dataset used in this research is not big, so we should wait several years to make it big, or we can use synthetic techniques and synthesizing techniques to make our dataset big. In order to do that, we have used statistical Monte Carlo simulation techniques to make our dataset big. And to conduct these experiments, we have used random forest algorithm. And to conduct these experiments, first of all, according to Kim 2017, first of all, we have divided the features to two categories: design features and process features. Design features are features that are related to design engineer, and process features are features that are related to job shop level. So, when design features are determined or the values are designed, then these features are fixed, and we have no control over these features after designing these features. So, we will have just 3 different features in RSW applications that can be controlled after fixing design features. These features are weld force, weld current, and weld time. To sum it up, after designing a weldment, we have two kind of features: design feature and process features. Design features are fixed after designing process. However, process features can be controlled by weld engineer or the technicians even after design features are designed. So, the random forest is trained based on design features and process features given in RSW AHSS dataset. Then, by using Monte Carlo techniques, we vary these process features to create different nugget widths. So, by doing this process, we increase the size of our data from 913 instances to millions and millions of instances. So, by conducting this experiment, we have created a synthesized dataset to conduct our experiments. The results of Monte Carlo analysis are here. We created different data sets at different levels. We coded the levels as 1, 2, 3, 4. Level 1, the number of instances is around 9,000, and the size of data sets for trained set is 0.5, and for test set is 0.27. The rest of the data sets are listed here. The biggest one has 913,000 instances for train and 342,000 of instances for test sets. After generating our synthesized dataset, now is the turn to design our experiments. Based on design of experiments principles outlined in Montgomery Design of Experiment sourcebook, we have designed our experiments. We have used full factorial design with two input factors. One factor is size of dataset, and another factor is execution framework. Size of dataset, as mentioned in previous slide, has 4 levels, and execution framework has 2 levels. One level is R, and another level is data view. So totally we will have 8 different settings in this experiment matrix. Our response variable is implementation time in second. Implementation time is the sum of training and testing times. Also, in order to analyze variability of our observations, 3 replications per prediction is gathered. Results of this experiment are shown in this table. In some settings, as results show, R failed to analyze. Specifically, if you notice, data size is very significant because, as it can be seen, R failed to conduct analysis at data sizes at data levels 3 and 4. However, data view conducted the experiments and were successful in analyzing in these 2 levels. So, R failed in some big data settings, and no numerical values are available for these settings. In order to analyze our experiments, we have 2 strategies. First, unbalanced experiments that will not yield an ANOVA table, and this is because some of the observations are NA or not available because R failed to analyze. Another strategy can be assuming that R conducted the experiments, to assume that R was successful, however, at higher costs with respect to data view. Let's say 10 times of costs. For example, if it cost for a data view to conduct an experiment in 1,000 seconds, it is assumed that R conducts the experiments, but at 10,000 seconds, not 1,000 seconds. By considering this assumption, we'll be able to create our ANOVA table and analyze the experiments. For the case of unbalanced experiments, we can use sum of square analysis. Sum of square analysis reveals that huge portion of sum of squared errors are due to size of dataset. So statistically, size of dataset is significant in these experiments, and only around 14% are attributable to execution framework, and there is no interaction between these 2 factors. Considering these results, we can infer that both size of dataset and execution frameworks are statistically significant. However, their interaction is not statistically significant. On the other hand, by using the second assumption and having values for failed scenarios, we can observe that the p-value of this ANOVA analysis reveals that execution framework, size of dataset, and execution and size of dataset interaction all are significant from a statistical perspective. So, execution framework matters, size of dataset matters, and selecting their combination also matters in big data scenarios. Here are the results of experiment analysis. First of all, main effect analysis shows that mean time of implementations in R and data view differs. Specifically, it can be observed that Mean time for implementations in R is significantly higher than mean time of implementations in data view. And also it can be observed that by increasing size of data set, mean implementation time increases, and there is a limit, a critical size of data set that that beyond this size, implementation time will increase dramatically. This can be observed in this chart as well. Mean time of implementations increase by increasing size of data set, and also implementation framework is important. For example, it can be observed that for lower dataset sizes like level 1 and level 2, it doesn't matter, or it doesn't statistically matter, which implementation platform is chosen. If you notice, these are small datasets, level 1 and level 2. So it doesn't matter R is chosen or data view chosen. However, for big data scenarios like 3 and 4 levels, there is huge amount of difference between R and data view in terms of implementation time. And data view has lower mean times of implementation. So based on this statistical analysis, it can be proved that data view defeats R in big data scenarios. Results and conclusion of this thesis. This thesis focused on design and development of scientific comparison of predictive performance of PWAs, design and development of a deep neural net as our contribution to RSW operations, and extending our research to big data scenarios. Several models included in our pool and were compared scientifically, a job that was not conducted before in the literature. It is shown that DNN models outperform other shallow models in terms of accuracy and variability of predictions. Also, it is shown that there is a critical value for size of data set, that beyond this critical value, changing implementation platform from in-memory platforms like R to distributed platforms like DataView is required. Our future works will be focusing on performance assessment of models in classification tasks. As it mentioned in this research, we just focused in regression tasks, and we don't know which model performs better in classification tasks. Another extension and another direction for our future work is assembling of PWAs in the hope of improving the prediction performance. Thank you very much. Any question?